Alright, I hope this is working. This is Mr. Fisk, and it is Wednesday. See, is it Wednesday? Yeah, it's Wednesday, the 27th of March 2013, and I'm not here. And we're doing notes on page 2 of unit number 9, and it is killing me not to do this one live because I absolutely love teaching this section. And so let me kind of zoom in here a little bit, see if I can kind of mess with my camera to make sure that it's zooming and focusing. So we're on page 2, and right in the middle of page 2 where it says gravity. Now I know that we didn't finish the boxes at the very top, and you're just going to have to kind of deal with that for right now. We'll come back and cover those when we come back after break. I'm just working on trying to focus this thing a little bit right now because it's not wanting to focus very well. That's about as good as that's about as good as I'm going to get. Alright, so we're on... Okay, so I guess I want to tell you, we're not going to finish the 4 forces in nature right now. We're going to finish those when we come back from break. I'm going to start with gravity right in the middle of page 2, and I'm just going to move from there. We're not going to hit everything. There are, I think, if I get far enough, there are a couple videos that are there. And we're not going to do those, obviously. Can't really do the video here. And some slides, and there's some concepts that are a little easier to do with me live as opposed to doing it through video. So I'm not going to hit everything, but I'll hit a majority of stuff. And anything that I miss, we'll come back and clean up after break. So hey, just a reminder that test is tomorrow, 4th hour. If you need more time on the test, you're going to have to come in right after chapel, or right after chapel and not dilly-dally, and get in and get started. And same thing for 6th hour. 6th hour, make sure that if you need some extra time, you're going to get in here during lunch. You can bring your lunch with you, get started, get cruising. But just a heads up, it's non-negotiable. When the bell rings, you have to turn in, come heck or high water. Anyway, here we go. We're going to take a look at gravity today. And it says right here, demonstration, attraction. And I guess I don't really have necessarily a demonstration for you, but I have maybe a Gedanken experiment. We're just going to basically talk about a couple of things. And I don't know if you know this, but I'm just going to throw it out there. And we'll start with 4th hour, and then I'll do 6th hour. Just want to let you know that in 4th hour, Austin and Sam are physically attracted to one another. Now, you may have kind of, may have been kind of suspecting that a little bit, but, I'm just making the announcement right now. Austin and Sam are attracted to one another. In 6th hour, I don't want to leave you out. 6th hour, Thomas and Joseph, you too are attracted to one another. I knew some of you were thinking the same, and I'm just announcing it for the world so that you all know this. And let's go back to, I don't want to leave the girls out, so let's go back to 4th hour. 4th hour, I'm not sure if you knew this, but Rachel and Sarah are attracted to one another. Been watching this for the past several months, and I've noticed it. Rachel and Sarah are attracted to one another. And 6th hour, don't want to leave you out, Alexa and Liz are attracted to one another. I'm not sure if you all knew that. They've been trying to hide it, but it's now out there. They're both attracted to one another. I can go a step further. If I were actually in this classroom teaching this live, I'm not sure if you've noticed this throughout the whole year, but the pencil sharpener in the back of the room, I've been attracted to that pencil sharpener in the back of the room. And that pencil sharpener has been attracted to me. I'm not sure if you noticed that, but that is the case. As a matter of fact, you can take this one step further. Anything that has mass is attracted to anything else that has mass. So if you look at the partner sitting at your table right now, you could look at the partner and say, hey, neighbor, you have mass, I have mass, We're both attracted to one another. How about that? That'll make you think. Guys, great pickup line. You're looking for a line. You could say, you've got this particular lady that you're interested in. You could say, hey, since you have mass and I have mass, you're attracted to me and I am attracted to you and we're attracted to each other. There's a good pickup line. So guys, as prom comes along and you're looking for that right moment, for that line, there it is. There's your line to pick up your prom date. It'll work. Trust me. Every time. So how does this all fit into what we're talking about with gravity? Well, there's way back when, in the 17th century, now I'm in your notes, I'm going to kind of fill some of this in as we go along now. In the 17th century, we have an explanation or a way of describing gravity. And Newton was the first one to sort of describe gravity. I'm going to see if I can get this even better in terms of focus. There it is. Okay. So in the 17th century, Isaac Newton, defined gravity. And here's what he said with gravity. I'm going to kind of pull this out a little bit, and let's see if it kind of stays focused for us. That's the best I got, gang. I'll try to read and say it, so if you can't pick it all up visually, I'll try to do it audio-wise. And he said this: anything that has mass, and anything that has mass is matter, I'm going to zoom in. Maybe this, tell you what, my document camera is just getting pretty pathetic lately, is attracted to anything else that has mass. And anything that has mass is matter. Anything that has mass is attracted to anything else that has mass. Pluto's like really far away. Pluto has mass, and so do you. And since Pluto has mass and you have mass, you two are physically attracted to each other. So here's what Newton was able to say about gravity. He was able to tell us how big it was, and hopefully if we get time today we'll do that calculation. He was able to share with us how far it acts, and he was able to say this: what effect it has on other objects. Now, we have a new definition for gravity, and this is where when I get back after vacation, I'll go through this new definition of gravity. But for right now, for the rest of this video, all you need to know is Newton's law, and that is anything that has mass is attracted to anything else that has mass. If we flip it over. Alright, this is on page 3. So the next question is this: if it's true that anything that has mass is attracted to anything else that has mass, then there has to be some factors that affect how much gravity exists between any two objects. You're on the clock. I want you to partner up, and I want you to brainstorm. What are 3 factors that affect the gravitational attraction between any two objects? You're on the clock. Ready, set, go. Fifteen more seconds. 10 more seconds. 5, 4, 3, 2, 1. All right, here we go. Let's go through them and see if we can agree. So somebody throw one out. Give me one. All right, good. Mass. And specifically, it's going to be the mass of one object. And then probably some of you were thinking, what was the other one? Okay, good. All right. It would be the mass of the other object. So mass of one object, mass of the other object. For example, if it was the gravitational attraction between you and Pluto, One of those masses would be you, and one of those masses would be Pluto. Okay? Now, let's go for the third one. So somebody throw out a third one. All right, good. I think I heard it in the back. Distance. The distance between the two objects. Okay, so there's three factors that affect it. Mass, mass, and then distance. All right, couple other things we need to kind of know about gravity. And the first one is this. That gravity is always an attractive force. It's never repulsive. So all the objects in the universe have mass, and so do you. So you are attracted to all the objects in the entire universe. I can just imagine what Joshicles is thinking right now and how many questions he has that he wants to ponder. Josh, you're just going to have to wait until we get back from vacation. I'm sure we'll have a big, long discussion, and I'm sure Mr. Barnhart will have a couple thoughts as well. All right, moving forward, here's the next one. The greater the mass of either object. So if you increase the mass of either object, the stronger the gravitational attraction between the two objects. In other words, all objects attract all other objects. Now, don't ask the sub to stop the video. You're going to have to kind of keep up with us, all right, as we go along. So if you miss a blank, you can pick it up later on. I think I'm going slow enough that you can pick this up. All right, attract all other objects in the universe. So as long as it has mass, it doesn't matter where it is, it's going to be attracted to each other. And the next one, the greater the distance between the two objects, the weaker the gravitational attraction between two objects. So if you see Austin and Sam sitting at the lunch table, or if you see Thomas and Joseph sitting at the lunch table eating, you know that their attraction between each other is going up. And if you see them sitting next to one another, their attraction is going up. Because the more mass you have, the greater the force of attraction between the two objects. You can think of it this way. Let's say, guys, you're looking for maybe a place to go out to eat. This nice new young lady, you're trying to, hey, got a place that, she says yes. Hey, all right, so we're going to go on a date. Where do you like to go? Take her to an all-you-can-eat buffet. Because here's the thought. If you can eat a lot and she can eat a lot, your masses go up. And if your masses go up, then your attraction goes up. So it can be an even more romantic experience. So probably the most romantic restaurants out there are the all-you-can-eat restaurants. This is just physics romance 101. All right, moving along through the video, we have a lot of cartoons, so there are the cartoons for you. All right, now Newton came up with a description and of his gravity, and all I'm going to do is I'm going to take all the concepts that we've been working with, and we're going to put them together into one relationship, and it looks like this. He said this, and I kind of screwed that up already. He said the force of attraction, I'll zoom in just a little bit. The force of attraction is related to, and I'm going to use the kind of the fish sign to show related to. Now we're talking about angular acceleration. Remember that for the test tomorrow. Okay. What we're actually talking about here is just a relationship. So the force of attraction between any two objects is related to the mass of one object, the mass of the other object, and the distance between those two objects squared. So let's think about it real quick. See if this makes sense. If you increase the mass of one object, the force of attraction between that object will go up. If you increase the mass of the other object, force of attraction between the two objects is going to go up. We totally got that. It's not a problem. Look at the distance. Now the distance is not in the numerator. It's in the denominator. So if the distance between the two objects increases, the force of attraction actually goes down. So the further you get away, the less the attraction. All right, moving on. this whole concept at the bottom of this equation, this d squared in the denominator, has a name, and it's called the inverse square law, moving down on your page. Alright, now the inverse square law, we just need to be careful with this. It's a really important law in science, especially physics. It's going to show up later on, and we kind of want to be aware of it. So I'm going to spend some time right now in the video just walking you through this. So here it is. I'll just give you the definition, and then we'll go through it, and I have a couple examples on the next page. So here's what it says. It says the inverse square law is a small change in the distance between any two objects makes a significant here's the next one, inverse. Okay, now what does inverse mean? It means reverse. So if one goes up, the other goes down. If one goes down, the other goes up. That's what inverse means. Change in the force of attraction between the two objects. I'm going fast now. You got to kind of hang in with me. And then, here's the other thing we need to know. The d or the r in this equation. Sometimes you'll see this equation written like this. Instead of using a d, you'll see an r in there as well. So, down back here, okay, here it is. The d or the r is the distance between the centers of the two objects that you're dealing with. I got two diagrams for you. Let's go through these two diagrams to make sure we're with this. So let's say this is mass 1 and this is mass number 2. The d, or the distance between them, is actually not the distance between their edges. It's actually the distance between their centers. Now, look at the next diagram. Kind of a crazy looking diagram. But we have someone sitting, no face, I'm sorry, no shoulders, no chest, no legs, just a face. But he does love physics. And right at the center is the center of this one. So if we were to say the d in this equation would be the distance between him and the center of the object. That would be d. Now, think about this. Quick question. How does the distance, let's see if this was the Earth, how does the radius of the Earth compare to maybe the height of his body? Well, it's basically whatever the height of this person is, it's insignificant to the distance between or distance of the radius of the Earth. Let me say that one more time. The height of the object is insignificant compared to the radius of the Earth. So in this case, the distance would be basically the radius of the Earth. Now, if you didn't pick all that up, that's okay. We'll kind of clean it up as we go along. All right, let's go to the next page. Page number 4. All right, it says example number 1. I'm going to do, let's see, how many are there? There's 1, 2, 3, 4, 5, 6, 7, 8. There's 8 examples. I'm going to grab a real quick drink here. All right, there's eight little parts to this. I'm doing the first part with you, just so you can get a feel for this. And then I'm going to let you kind of push through the rest of them and see what you can get. So here's the first one. It says, if the distance between the two objects is doubled, the force of attraction between them will be what? All right, now, I didn't give you a lot of room to work. So you're going to basically maybe use the margin here. You're going to be using this equation that we dealt with. This is Newton's equation for gravity. Getting ahead of myself. Alright, it's going to be F is proportional to M1, M2 over, now it's D squared, but you're going to find out in just a moment that it's going to be real important that we write, instead of saying D squared, we know that D times D is D squared. Okay, hopefully we've got that. You're going to find out that leaving those as D times D is going to be really, really helpful in just a bit. Alright, here we go. Let's do letter A together. It says that the distance between the two objects is doubled. Alright, now think about this. D is entered into the equation twice. So if we double one distance, we have to double the other distance. So I'll have a 2 right here and a 2. I'm coming back. Okay, there it is. A 2 in both places. So in reality, on the right-hand side of the equation, it's not a 2 downstairs, but it's a 4. And we know in math, if I divide the right-hand side by 4, I have to divide the left-hand side by 4. So over here, I'm going to come over and I'm going to divide by 4. So this force here is going to be 1/4 as much. So I'll put a 1/4 in the blank. How about I do one more, just so you can kind of see it one more time. I'm going to go down and do letter F. Here's letter F, just so you can see both of them working together. Ready? Here it is. If the distance between any two objects is doubled. Okay, well, we've got that right here. We doubled the distance, so that's good. This is letter F. And the mass of one object is doubled. So I'm going to come back up here. Now, this time, I'm doubling the mass. So if you take a look at this, but I'm only doubling one of them, I'm not doubling two of them. So this mass and this mass cancel out. So now, we're not dividing the right side by 4, we're actually dividing by the right side by only 2. So the force is going to be 1/2 as much. So the answer for letter F, I'll put it right up here on the screen, is going to be 1/2. I have a feeling even on this video you guys are confused right now. Let me do one more and then I'll let you cruise. I think if I do one more, you'll understand it. Let's do letter B. If the distance between two objects is quadrupled, what does quadrupled mean? Quadrupled would mean multiplying times 4. So now I'm just going to rewrite my equation because it's getting a little messy there. So there's M1, there's M2, and there's D and the D. Alright, this time I'm multiplying the distance by 4. But that distance shows up twice in the denominator, so I don't do it once, I do it twice. So if I divide the right side by 16, yes, 16, not 8, 16, then I have to divide the force. Gosh dang, I'm screwing up already. I have to divide the force by 16. So, letter B, the answer is 1/16. I'll leave it on the screen here. 1/16 as much. Alright, I did 3 of them. It's your turn now. Find a neighbor, partner up, let the video keep running, and I'll give you a few minutes to kind of walk through them. All you need to get down to is letter G. Don't worry about letter H right now. We'll talk about that one a little later on. Alright, a few minutes, partner up, ready, set, go. Keep going, keep working, give it a whirl, don't give up. Give it a shot. The best way to learn is to make an effort. And if you make a mistake, hey, we'll fix it here in just a bit. Keep it up. You're doing great. Give it another 30 seconds or so. Keep it up. Get all the way down. If you haven't gotten to letter F and G, give F and G a... Actually, we did F already. So give G a whirl. Alright, let's go through the answers and see how you arrived at them. So we did A and B already, so let's do C. C says that the distance between two objects is halved, and the gravity between. We'll just go through the answers first, and then if we need to talk about them, we'll talk about them. So if the distance between two objects is halved, the gravity between them will be 4 times as much. Who got it right? Who got it right? Good, nice job. All right, the next one, letter D. If the mass of one object is doubled, and the gravitational force between them, the gravitational force between them will be 2 times as much. Who got it right? That was a little easier one. Good, good, awesome. All right, the next one, letter E. If the mass of one object is doubled and the mass of the other object is halved, the gravitational force between them will be. Good, I heard it out there. I think some of you got that. Nice job. Same. Okay, or the same as much. I don't know, my blanks don't work out real well there. You just kind of have to deal with it. All right, let's do letter G. Letter G. If the distance, where's my scholars? A students, let's see what you got. If the distance between any two objects is tripled, and the mass of one object is halved, the force between the two objects is how much? Good, nice job. It is, oh, I can't read my own writing. I think it's 1/18. I think it's 1/18. Anybody get 1/18? All right. All right, so any questions? Any of them that we need to see? Okay, I'm hearing that we need to do letter C. So let's do letter C real quick. That one, yeah, that one's a little bit tougher. So I'll do letter C here up on the screen. Let me focus in just a little bit. And I'll do letter C for you. So here it is. So F is proportional to M1, M2 over D and D. And what's happened on letter C? Letter C, they say that the distance is halved. That means we got a half sitting here and a half sitting here. So now remember this. A half times a half is a 1/4, but that 4 sits in the denominator of the denominator. And if the 4 sits in the denominator of the denominator, it really means it sits in the numerator. So it's really 4 times the force. Any others that we need to do? Okay, I heard letter G. Let's do letter G real quick, and we'll see how that one. This will be my last one that I do. Some of you guys have questions on the rest of them. You can ask me when we get back from break, and I'll be more than happy to go through it with you. Let's do letter G. G says this. If the distance between any two objects is tripled, okay, now distance is tripled, so that means I got to put a 3 in there. And the mass of one object is halved, so we got to put a half right there. The force between the two objects is 1. Oh boy, what's this? Let's see, how's this going to work? I think I need to maybe work out on the side over here. So 1/2, so that's just going to be like a half in the numerator. 3 times 3 is going to be 9, but it's like a 9 over 1 in the denominator. So if I invert and multiply, there it is, 1 over 18. We were right. So there it is, 1/18 there. So we have to divide the force over here by 18, and there it is. That's called the inverse square law. And you'll see the inverse square law come up anytime we have a d squared in the denominator. Very good, nice job. All right, moving on through the notes. I have an extra credit question for you. We'll eventually get there when I get back. So we're going to skip over that. We'll skip over the Hewitt DVD. I know. Deal with it. Cartoon we'll show you a little later on. Let's talk about Newton's success and an issue that he kind of had on some of this stuff. So here it is. We'll go through it. So Newton had, when he came up with his law, he had one problem. He could only establish a mathematical relationship between the masses, the distance, and the force. So all he could say was, hey, if I got a big mass, I got a big force. If I got a big distance between them, I got a small force. That's all he could say. He couldn't calculate it. So he could not, I'm moving back in your notes, he could not convert the mathematical relationship into a mathematical equation. To convert the relationship into an equation, a constant, and that constant has a name. It's called big G, as opposed to little g. Little g is the acceleration of gravity, okay? Called big G must be determined and introduced into the equation. This required technical equipment that was not available to Newton. Alright, so let's see if we can kind of think through what the issue was here. Newton said this: if you have a mass, m1, and you have another mass, m2, and you knew the distance between them, then there was this relationship that he came up with. And the relationship looks like this. I'll zoom in a little bit here. The relationship we said was m1, m2 over d squared. But here's the problem. This is not an equal sign. And if it's not an equal sign, then we can't figure out what this force is. To convert it to an equation requires us to add in what's called a constant. And that constant makes the equation look like this. F equals, now it's an equal to, G m1 m2 over d squared. As soon as I know what this is, okay, so think about it this way. If I knew what this was, if I knew what number that was, then I could take that number times the mass, divide by the d squared, and I would know the force of attraction between those two objects. I would be there. Home run. Very good. But here's the problem. Newton died without ever determining that number. He couldn't figure it out because he didn't have the equipment necessary to figure that out. Well, there was a guy by the name of, and I'm in your notes now, in 1798, 71 years after Newton died, Henry Cavendish calculated the value of big G by accurately measuring the mass of both objects, the distance between them, and the force of attraction between the two objects. Now, when we get back from break, Hewitt's got a wonderful DVD that kind of shows how this worked out. I'm not going to go through all the details right now on the video, but Hewitt will, and he'll go through it, and when you watch it, it'll be crystal clear, because we all know that Hewitt's great. Flip it over. So in example number 2, we're going to actually run this little experiment. So we're going to use, I'm just going to read it off to you here, example number 2. We're going to use the following data to simulate Cavendish's experiment by calculating the value for big G and its units. The force of it, so here's what he did. He said the force of attraction between two objects having masses of 12 kilograms and 25 kilograms, and these two objects are separated by 1.2 meters. He calculated that force. How that worked out, Hewitt's going to explain that. But the force became 1.4 times 10 to the minus 8 newtons. All right, so diagram time. Here's two objects. This was 12 kilograms. This was 25 kilograms. They measure the distance between their centers. There's the 1.2 meters. And then the force of attraction between these two objects was calculated as 1.4 times 10 to the negative 8th newtons. Alright, so let's take this one step further. So we have the equation that Newton started out and then Cavendish kind of finished off, and there's the equation right there. Think about this. If we know F, M, and D squared, we can calculate G, and that's what Cavendish did. So let's take this equation, let's rearrange it for G. So G, then if we solve for G, it's going to be F d squared over m1 and m2. Alright, so let's plug the numbers in. We got them all. Let's do it. So the force of attraction between the two objects was 1.4 times 10 to the minus 8th newtons. The distance between the objects was 1.2 meters, and we squared that. And the two masses, one was 12 kilograms, the other was 25 kilograms. Alright, take a moment. Brad, I know you have your calculator. I have confidence. I'm confident. Plug in those numbers. Let's see what we get. That includes you too, Barnhart. Punch, punch, punch. Do it, do it, do it, do it. Plug it in. When you get it, check your neighbor. That's what we do in science. Verify your answers. Alright, if you did it correctly, you should have come up with a number that looks like this. 6.72 times 10 to the minus 11th. How many people got that? Alright, if you didn't get it, don't forget to square the 1.2, and then when you divide by 12, you have to hit the divide button again to divide by 25. So just a heads up there. Alright, now let's do the units, and then we'll wrap this up and the video will be done. Alright, so here it is. Big G, 6.72 times 10 to the minus 11th. Now let's just think this through. On the numerator, we have a newton and a meter squared, and on the bottom we have a kilogram squared. So the units are newton meter squared over kilogram squared. And if you take out your orange sheet real quick, pull it out, go to the constant sheet, thumb through, you're going to find that the number for big G is actually not the number you see up here on the screen. It's actually, if we were to sharpen this up, it's 6.67, this is the number I want you to use, times 10 to the minus 11th newton meter squared over kilogram squared. And there it is, that's big G. So last couple blanks. The units in big G demand that all masses be measured in kilograms, time measured in seconds, and distance measured in meters. And we will do this last star together when we get back. Gang, have a great Easter. Test is tomorrow. Problem sets will be collected. So just a heads up, problem sets will be collected. And I also noticed that I didn't think through the logistics on this one. I'm not going to collect your multiple choice sets until we get back after break, because I know some of you have given me your multiple choice set and have not done your Scantrons, and so and I have your multiple choice and you're not getting them back right now, so because I'm not here. So the only thing that we will collect tomorrow is problem sets. So you can, for right now, just take the multiple choice, move that off, and we'll collect that when we get back. Otherwise, have a great Easter. Good luck on the test tomorrow, and have a great day. Your name. Here we go. See ya. Have a great day.